Start at 1. Notice number 1. What's the derivative of the inside?
3.
Yeah, and that's the multiplier. Now, let's just go through the process, because I think this is important to actually go through the U substitution. Okay, so in other words, we have the integral set to the 5th.
Yeah.
If we had to come up with a U, what would it be?
3x minus 2.
Yeah, U is equal to 3x minus 2. Now, the whole concept with U substitution is we're going to take this integral that is in x, and we're going to change it to an integral in U that we can do. We don't really know how to do this integral. Okay, in other words, integration is a lot different than differentiation. You have 4 rules that work all the time in differentiation. You have the power rule, you have the product rule, you have the quotient rule, and you have the chain rule. But integration is a whole different story. If you can use the inverse power rule, then it's really easy. But when you get more complicated functions, it becomes really tough. Okay? So, the first thing you do in U substitution is find du dx. What is du dx equal
to? 3.
So, du is equal to 3 dx, and dx is equal to du divided by 3. Okay? Understand all of those steps on the right side. You with me? So now this integral becomes 3 times u to the 5th, and in place of dx, I'm going to substitute du over 3. And now the 3's cancel, and I have an integral that I can do. What's the integral of u to the 5th du?
U to the 6 over 6 plus c.
Okay. Now we go back and resubstitute. Our u was 3x minus 2. So our answer really is 3x minus 2 to the 6th divided by 6 plus c. And there is our answer. Okay? Now, let's look at this problem. They may have neglected to take this last step. And it's the way most calculus is taught these days. Let's just go through this problem again. And instead of doing this last step, let's erase it. And we know that du is equal to 3 dx. Okay? Well, if I look at my integral, I'm looking at 3 dx right there, just not next to one another. But that, the associative property still holds. So I can immediately, instead of writing all of that, I can immediately say u to the 5th du. Why? Because the 3 dx is equal to du. So it kind of saves a step.
All right.
Okay. The answer is the same. In other words, we still end up with u to the 6th over 6 plus c. And then we resubstitute. and we get 3x minus 2 to the 6th over 6 plus c. Okay? So these other problems, let's do without doing that final step. In other words, let's do them directly. Well, what's u going to be here?
5t minus 3.
What's the next step?
Um,
In other words, we can't use the reverse power rule here. We can't just add 1 to the exponent and divide by the new exponent. That's not going to work because there's an inside. Remember that whatever we come up with, if you take the derivative of it, it has to equal this. Okay, so let's just talk about that for a second. Let's just say I tried the reverse power rule. Right?
mm-hmm.
Okay, now let's take the derivative of this and see if we get the answer. Well, the derivative is what? It's 9 times 5t minus 3 to the 8th all over 9. But then we have to use the chain rule. So we have to multiply everything by 5. Well, notice I don't get the same thing. I get 5 times 5t minus 3 to the 8th. Well, the whole thing about integration is that you have to be able to take the derivative of the integral and come up with the function that you started with. Well, the function we started with was 5t minus 3 to the 8th, and using just the reverse power rule, I didn't get that. So that's why we cannot use just the reverse power rule.
Okay.
So du dt equals what?
5.
What's du equal?
5 dt.
Now, do we see a 5 dt anywhere? No.
No.
We see a dt. So now this requires a little bit of out-of-the-box thinking. Okay? The one thing about integrals is that if you have a constant, you can always place it inside or outside of the integral. So if I need a 5 there, I can just stick it there and stick a 1/5 out there. With me?
Yeah.
Now I've got my 5 dt that I can replace with du. So the integral in u becomes u to the 8th du. Now here's the thing about integrals. You can only integrate one variable. You can't have an x in there. If I had an x in there, I do not know how to integrate that. So the trick when you're doing U substitution is to end up entirely with an integral of u, because what's the next step? What's that?
You do u to the 9th over 9.
Okay, I'm still multiplying by 1/5. And now resubstitute. What is u?
It would be 5t minus 3.
To the 9th, all divided by 9. There's your answer.
So you can just bring that 1/5 back in.
Well, you can't ignore that 1/5. And notice that let's do this problem a slightly different way because I want you to see this. I think this is really important in understanding. Notice that if I did the last step that I said we're trying to shortcut, I would have du over 5, right? So now I can just go up here and say, well, that's u to the 8th, and dt is du over 5. Well, now I can take that 1/5 out, and I end up with the same thing. In other words, you can always take constants out. You can't take variables out of integrals, but you can take constants. So I get to the same exact spot that I got before, but I kind of had to, I hesitate to say do an extra step. I had to do this step here, and it will become more apparent to you as we go through these why that's the case. Now, number 3. What's the inside going to be?
4 minus x cubed.
What's the derivative of the inside?
3x squared.
Minus 3x squared.
Oh, minus 3x squared.
Which means du is equal to minus 3x squared dx. And let's go ahead and do that last step, because I'm convinced this helps in understanding it. Notice that the derivative of the inside almost always ends up in the denominator, which is great because we have an x squared there that we don't know what to do with. In other words, I've got x squared over the square root of u, and now dx is actually du over minus 3x squared. You with me? Now my x squareds are going to cancel, and I have an integral that I can do, which is 1 over minus 3 times the square root of u du. Okay? I can do this because I can express it as a single polynomial. I can take the minus 1/3 out, if that makes you deal with it a little bit better. And you have u to the minus 1/2 du. With me?
Yes.
Take the integral of that. Now you can use the reverse power rule. What do you get?
U to the 1/2, well, 2u to the 1/2. And then you multiply that
by the negative 1/3.
Yeah.
Now u is 4 minus x cubed, so this is negative 2/3 times 4 minus x cubed to the 1/2. Okay? Now, if you really want to know whether you did your integral right, what do we have to do?
Take the derivative.
Okay, let's take the derivative of that. Let's see what we get. Where do you start with the derivative?
You put the multiply by 1/2 in the front.
Right. So we have minus 2/3 times 1/2 times 4 minus x cubed to what?
To negative 1/2.
Okay. And then we have to apply the chain rule. So what's the derivative of the inside?
Negative 3x squared.
Now the question is that what we started with? Well, let's see. Let's take away that negative sign and that negative sign. Let's take away that 3 and that 3. Let's take away that 2 and that 2. And what am I left with? I have an x squared in the numerator, and I have a square root of 4 minus x cubed in the denominator. Is that what I started with? Exactly.
Mm-hmm.
So that's always a check. In other words, until you're really, really confident in doing this, I would suggest always doing that check. Once you get to the point where you're pretty comfortable, then maybe you don't need to do it every time. Okay?
Okay.
Now, let's take this one again. What's the inside?
X cubed minus 1.
No. Oh, excuse me, yes. What's the derivative of the inside?
3x squared.
Notice that we have a 3x squared in the numerator multiplying that. That's what we're always looking for. We're always looking for that, which is a composite function, times the derivative of the inside. Now, you know what I mean by a composite function?
Not really.
If I have f of x equals square root of x, and I have g of x equals x cubed minus 1, and I put the two of them together in a composite function. This is stuff you learned in precalc, so it was like last year.
Mm-hmm.
Okay, well, that's what? Hold on 1 second, Jackson. Let me go down and turn my sound off. I'll be back in a minute. Sorry about that. I forget when I pause my TV, it comes back on automatically 30 minutes later. So what would f of g of x be?
Would it be?
It would first of all be f of x cubed minus 1. Right? That's what g of x is?
Right.
So what's f of x cubed minus 1 if f of x is square root of x?
It'd be root x cubed minus 1.
Yeah. Notice that's what we were looking at. We were looking at a composite function. In other words, when you see something like this, where you're going to have an inside, you're looking at a composite function. If in the perfect scenario, this is being multiplied by g prime of x, then you have a perfect U substitution problem. If I say, have you had trig function derivatives yet? You have, right?
Yeah.
If I have this, they teach you to do something called pattern recognition. In other words, here's what's going to happen. By the time you learn all of calculus, you're going to have like 7 different methods to integrate something. At the moment, you've only learned 2. Okay? Well, what you have to do is recognize an integral as being something. Well, notice that this is a composite function, and that's the derivative of the inside.
Mm-hmm.
Whenever you have that situation, it's perfect for U substitution, and let me show you why. Here, let me close this because I really want to cover this. What's U going to be?
Cosine x.
No, sine x.
Sine x.
Right, sine x. Why? Because I want to write this as u to the fifth. That's my goal.
Okay.
Okay. What's du dx?
That'd be cosine x.
What's du?
Cosine x dx.
What's dx?
Du over cosine x.
Notice that the derivative of the inside, again, is in the bottom. So now when I rewrite this, it's u to the fifth times cosine x, but in place of dx, I have to write du over cosine x, which is perfect because it gets rid of the x variable. Remember, you cannot take an integral of u if you have an x variable in there. So now it's real simple. The integral of u to the fifth du is equal to u to the sixth over 6 plus c. Now I go back and substitute for u. It was sine x. So my answer is sine to the sixth of x over 6 plus c. So what we're always looking for in order to use U substitution, and in all honesty, this might only be like 5% of functions.
Mm-hmm.
You know, in other words, when you're looking to integrate, integration is an unbelievably difficult thing. For thousands of years it has been. And they've always looked for a simple method to do it, and they've never really had one. Like I said, there's 7 methods of integration, and each one is tougher than the previous one. This is actually one of the easier ones, U substitution. And what you're always looking for is what would the inside be? If you were going to differentiate that, the inside would be sine x. So whatever you would use for the inside to differentiate it, use for u.
Okay.
Same thing. And you want it to be being multiplied by the derivative of u. And it doesn't matter whether there's a number in front of this or a sign that isn't right, you can always make that right. In other words, it doesn't have to be exactly cosine x. If it could be cosine x over 2, I'd still be able to handle that because I could take that 1/2 outside. I can make it look like that, and then I've got the perfect derivative right there.
Mm-hmm.
All right, let's do some more and see whether you're picking up on this. Notice what's going on here. What's the derivative of the inside?
2y.
What do we have being multiplied by?
Y dy.
Right. So all I need is a 2 in front of that, and everything's perfect. So I've got the integral, and I'm going to change all radical signs to exponents because exponents just work better, given you have the power rule.
Mm-hmm.
So and you don't always have to go through this U substitution. Sometimes all you need to do is just recognize that the derivative of the inside is 2y. So if I have a 2y there, I can just straight use the power rule. But I don't have a 2y there. So u is equal to y squared minus 3. What's du equal to?
2y.
2y dx, or dy, excuse me. There's no x's, it's just y here. Well, now instead of doing this last step where I define dy, I'm going to try to save time. And I'm going to look for a 2y dy. Well, we've got a y dy, and I can easily stick a 2 in there as long as I stick a 1/2 out there. With me?
Yeah.
Okay. Now I can turn it into an entire integral in u. This becomes u to the 1/2, and this 2y dy becomes du. So what's the integral going to be?
U to the 3/2. Well, 2/3 that times 1/2.
Equals 3u to the 3/2, I believe, plus c equals 3 times y squared minus 3 to the 3/2 plus c. I do everything right there. Let's see. I multiplied by 2 over 3. And I think I got my 3 in the numerator instead of the denominator. Let's see. This should be 2/3, as you stated when you gave me the answer. Yeah, my 3 is in the denominator, not the numerator.
It should be 1/3.
Yeah. There's your answer. And if you were to take the derivative of that, you would find that it equals y squared minus 3 to the 1/2 times y. In other words, whatever you started with.
Okay.
Okay? Now, I'm going to skip forward for a moment. I love what they're doing here. They're giving you about 10 of these to practice on. But let me just show you an exception. Let's say I want to integrate that. In fact, let's make it easier. Let's make cosine. Okay? Now, what would u be?
Would it be cosine?
No. If you were differentiating this, what would u be? What would the inside be? The outside is cosine. What's the inside?
Maybe ln x?
Yeah, natural log of x. What's du dx?
It would be, let's see.
This is one you want to memorize. This comes up a ton in calculus, especially in integral calculus. It's 1 over x.
I don't remember.
The integral of natural log of x is 1 over, excuse me, the derivative of natural log of x is 1 over x. Okay? Well, if you go through this, we now have this dx over x, which means dx is actually equal to x du. The derivative didn't end up in the denominator like every one we've looked at. It ended up in the numerator. Okay, so, excuse me, let me add something to that I didn't have in there before. In order to use U substitution, I need this x in the denominator. Why? Well, let's go through it. Cosine of u, that's what natural log x is.
Yeah.
And then dx, if I solve for dx, it's x du. So if I want to substitute for dx, it's x du. And I still have this x from the original problem there. Well, my x's cancel, and I have something I can integrate. In other words, now I have cosine u du, and I'm in clover. Once you get the entire integral in u, and it's a simple integral, you can integrate it. But notice the difference here. In this problem, I had the derivative of the inside was in my denominator, not my numerator. 95% of the time, the derivative of the inside is going to be in your numerator. But there are some functions, like natural log of x, which are going to put it in the numerator instead of the denominator. And so when you're looking for your pattern recognition on these kind of functions, you're looking for the derivative of the inside to be in the denominator. Then you can use U substitution. It's complicated, but that's kind of what you're looking for, is where is the derivative of the inside? Well, if we look at number 5, what's the derivative of the inside? What's the inside, first of all?
Well, so is number 5 one of those where you could just bring the bottom to the top and then like multiply it out, then use the power?
The more important thing, yes, you could do that. Well, no. The most important thing is that you know what U would be.
Okay. Well, would it be x cubed plus 2?
Yeah.
Okay.
In other words, it's usually the obvious. X cubed plus 2. That's going to allow us to write that as U to the 6th. We can integrate that. But more importantly, what's the derivative of the inside?
3x squared dx.
Yeah. And it doesn't matter that this says 5x squared. What's important is that it says x squared. In other words, we need the degree of the variable to be the same as the degree of the derivative of the inside. It doesn't matter that that's a 5 and we're looking at a 3. I can handle any change in constant. What I can't handle is if this said x cubed. If that said x cubed, this would not be a problem for U substitution. It would be a problem for some different type of integration method. It's only a problem for U substitution if the derivative of the inside is the same degree. Okay, well, let's carry this forth and say that's 3x squared dx. So this time I'm going to go ahead and do the 4th step just because it's a little more complicated. So that's the first things you do. Okay, when you're looking at this. Now, let's see how much of this we can rewrite as U.
Okay.
5x cubed is just 5x cubed. I'm going to leave that.
Wait, is that x cubed or x squared?
Excuse me. Thank you. For the moment, I'm going to leave that there.
Okay.
What's the bottom become?
Just u to the 6th.
What's dx become?
Du over 3x squared.
Now the most important thing is I got rid of the x variable. So now I have 5 over 3 u to the 6th du. That integral I can do.
Mm-hmm.
Let's take the 5/3 out just to make it a little simpler. Let's write it as u to the minus 6 du. Same thing. What's the integral of that?
U to the negative 5th over negative 5.
Still have to multiply it by the 5/3. 5's cancel, and I get u to the negative 5th over 3. Still a negative sign in there. And now I resubstitute. It's always the last step. U was x cubed plus 2. It's now to the minus 5th over 3. And if I want to write that in the manner they gave it to us without negative exponents, but with positive exponents, then it's minus 1 over 3 times x cubed plus 2 to the 5th plus c. Okay, so again, they gave us a problem where the derivative of the inside was in the numerator. And that's what you're going to see most of the time. It's going to be the hard problem where the derivative of the inside is in the denominator, which is the case I covered. But, alright, so here, minus 3, and let's write this as 1 minus v to the negative 1/2 dv. Okay? The derivative, in other words, is this a problem for U substitution? What's the derivative of the inside?
Just be -1.
Yeah, which means it is a problem for U substitution. In other words, it's nothing but a constant. Constants I can handle really easily. Make this v squared, it's no longer a problem for U substitution. Notice that the derivative of the inside is now minus 2v, and I don't see any v's anywhere else. So I would not be able to use U substitution on that. But as long as the derivative of the inside is a constant, then let's go ahead and use it. With me?
Mm-hmm.
Okay, so what's this become?
Would it be here?
Go ahead and put the minus 3 in there.
Okay.
What's the rest of it?
U.
What's dv become?
Du over -1.
Now these negatives cancel. I can take that 3 outside, and I'm left with this. Right? What's the integral of that?
Be u to the 1/2. Well, so 2u to the 1/2 times 3.
Okay, and u was 1 minus v, so that becomes 6 times 1 minus v to the 1/2, or if they want it in radical format, it's 6 times that, plus c. You always have a plus c when you have an indefinite integral. An indefinite integral is where I do not have limits of integration. I don't have going from 0 to 2 or from -1 to 10. Okay? This is called an indefinite integral. If I have limits of integration, it's called a definite integral.
Mm-hmm.
Whenever you are taking an indefinite integral, you always have this c. And the reason is that if I differentiate that, the c disappears. If I differentiate this whole thing here, I'm going to end up with that. Exactly what I started with.
Okay.
Okay? Now, I think at this point, I see some problems here that are a little different. I was going to say, let me explain a few other things to you, but what's the derivative of the inside on 7?
Would it be 4x minus 3? No.
Exactly what it's being multiplied by. So the only thing we need to do to integrate that is to use the power rule. Ignore that. That's going to go away. So the answer is 2x squared minus 3x to the 5th power divided by 5 plus c. In other words, whenever I recognize the pattern that I have a composite function, the derivative of the inside is multiplying it, then I can just use the power rule on this part of it. That's all I have to do.
And that works for everything that applies to that?
Yeah, it really does. What's number 8? What's the derivative of the inside in number 8?
4x minus 4?
No. Oh, excuse me. Yes, 4x minus 4. Notice I can factor a 4 out, and I have x minus 1. Well, I got this weird x minus 1 up here I got to get rid of. I got to deal with somehow. Well, knowing that the derivative of the inside is going to end up in my denominator, I know the x minus 1 is going to cancel with that x minus 1. So I can almost just use the power rule on this, but I do have to allow for that 4 there. But like I said, constants are really, really easy to allow for. Now, before we go on, there are 2 main types of U substitution. The one we've been doing today, and there's another one that's called change of variable. Notice this one here. Well, if I had an inside, it would be x plus 1, right?
Yeah. The
derivative of that is 1. Well, that's not what's in my numerator. How the heck do I integrate this thing? In other words, this does not fit this pattern. That's the main pattern you're looking for when you're doing U substitution, is a composite function multiplied by the derivative of the inside. Well, that's not what we're looking at here. But why is this hard to do? If I had a plus b over c, it would be easy to do, because that would be the integral of a over c plus the integral of b over c. But when I have 2 terms in the denominator, I cannot split it up. In other words, x over x plus 1 is not equal to x over x plus 1. Well, excuse me, it's not equal to x over x plus x over 1. You cannot split up fractions like that when you have 2 terms in your denominator.
Okay.
If I have x plus 1 over x, different story. That is equal to x over x plus 1 over x. Okay, so that's the main distinction you need to be able to make, is that when I have that kind of fraction, I can split it up into 2 fractions, but when I have 2 terms in the denominator, I cannot. Well, look what happens when I use U substitution. Now this is called U substitution, but it's really completely different. What's du dx?
1.
Which means du is equal to dx. But if u is equal to x plus 1, what is x equal to? Here's the step that we have not been doing in any of the others.
U minus 1?
Right. Now watch what happens. Now when I go to substitute, x is u minus 1, x plus 1 is u, dx is du. Now that I can split into 2 fractions, because I only have a single term in the denominator. So this is equal to the integral of u over u minus the integral of 1 over u. You got that? In other words, the beauty of integrals and derivatives is the integral of the sum is the sum of the integral.
Mm-hmm.
Well, once I've turned this into two integrals, now I have the integral of just du minus the integral of u to the minus 1 du. What's the integral of du?
U to the
Just 1.
1.
What's the derivative of 1?
Okay.
Excuse me. It's u. What's the derivative of u? 1.
1. Okay.
This is basically the integral of 1 du. So the integral of du is u. What's the integral of u to the minus 1?
U. So 1.
Well, let's try the power rule. What happens when I use the power rule?
You get u to the 0 over 0.
Ah, that's trouble. Can't divide by 0 in math. So this particular integral you cannot use the power rule on. That's the natural log of u. Remember what the derivative of natural log was. It was 1 over u. So the integral of 1 over u is natural log of u. Plus c. Okay, well u was x plus 1. So my answer is x plus 1 minus the natural log of x plus 1 plus c. And it was U substitution, but it was U substitution that they call change of variable. In other words, this was actually a different category of U substitution. There's two categories. There's the one where you have f of g of x times g prime of x, and then you have the one where it's just called change of variable, where I don't have any kind of g prime of x times f of g of x. But if I just let u be the complicated part of this function, it works out pretty nice. I turn it into an integral that I can do. I can do this integral. I can't do this integral. And just so you know, there's all kinds of integrals that cannot be done. There is no antiderivative for a lot of functions. If I look at this function here, there's no function in the universe whose derivative is that. So when I go to take an antiderivative or integral, you've used the term antiderivative, right?
Yeah.
Okay. If I'm looking for an antiderivative and one doesn't exist, well, integral means area under the curve. Okay, well, this curve maybe looks something like that. So there has to be an area under that curve. So there must be an integral to this function. I just don't know how to do it because there's no antiderivative. Well, guess how you do it? You use infinite series. And that's probably the hardest method of integration there is. I mean, that's like a 3-month course. Infinite series. And I'm not kidding you. That's how hard it is. Jeez. But what you do is you substitute an infinite series for that expression, and then you have an integral of x plus an integral of x squared minus an integral of x cubed. In other words, once you substitute an infinite series for that, now you have a bunch of sum and differences of integrals that you can integrate. but it's still an approximation. In other words, we have no exact way of figuring out this answer. It's at best an approximation. There are some functions that only have approximations as their integrals. And when you put in your integral into your calculator, do you have a TI-84 or an Inspire?
I think I have an 83 one.
Okay, that's all right. It still does integrals, numerical integrals. It's using approximations every time it does that. It does not know how to do it exactly. We know how to do this. When I say that, and I say evaluate it between 0 and 3, I know how to do that exactly. Your calculator does not. Your calculator uses an algorithm that merely approximates that. So if you're wondering why we learn how to do integrals when our calculator can always do them, calculator's always approximating it, whereas we frequently can come up with exact answers. Now, for this kind of an integral, we can't even come up with an exact answer. We can only come up with an approximation just because of the nature of the function.
Okay.
Okay. Look at 14.
Mm-hmm.
We don't need to use U substitution on that.
Right.
Why? Because I can break this into 3 integrals. It's this integral plus this integral minus this integral.
And that's the same for 13 too, right?
Well, I hadn't looked at 13. Let me look. Yes.
Right.
In other words, whenever you can break it down, well, now notice what we have. We have the integral. Well, what's 3x squared divided by x to the 1/2? It's 3x to the 3/2 plus this is x to the 1/2 minus this is minus 2x to the minus 1/2. Each one of these we can do using the power rule or the reverse power rule. So this is not a U substitution problem. It's merely turning it into 3 integrals instead of 1. And of course the dx goes with each one. Sometimes I forget to write it, but
okay.
Okay. All right. That's a good place to stop. And I've kind of covered all 3 U substitution methods. You got the method where the derivative is in the numerator. You got the method where the derivative is in the denominator. And then you have the change of variable method. And you not only have to be able to do them all, but you have to be able to recognize where you can actually use them. I had a student recently, and his teacher gave him this problem. To integrate. I took one look at it, and I said, she made a mistake. This can't be x, this has to be x squared. Because the derivative of the inside is 3x squared. The only way you can use U substitution on this problem is if the derivative of the inside, the power on the x, is the same as what's being multiplied. So I told the student to change the problem to that and go back and tell the teacher that she made a mistake and that this is what the problem should have been. Sure enough, he did that and she said, "You're right." You can use U substitution on that problem. If it's just x, you cannot use U substitution. You have to find some different method. Probably what I got to do is take this to the 8th power, multiply every term by x, and then integrate all 9 terms, or 18 terms, however many terms you have. But you cannot use U substitution on that.
Okay.
All right. Jackson, I will talk to you next Friday. Oh, well, let's see. Next week is Thanksgiving. You just have school on Monday and Tuesday?
Yeah.
You need a session on Friday or not? I don't care. I'm going to be around. So if you need a session, I can give you one. But it's up to you or you and your mom to decide whether you want a session or not.
Can I email you what we decide? Because I'm not sure.
I'll leave it on there for now.
Okay.
And then email me if you want to cancel.
All right.
Otherwise, I'll just plan on you being there, and I'll send you a meeting ID number at noon on Friday.
All right. Sounds good.
All right? Okay, Jackson. Talk to you maybe next week, maybe